Got a piece of vintage electronic gear that needs one of these now unobtainium mercury batteries? I've got a solution for you. Welcome back to Cloud42, I'm James. In a previous video, I recommissioned a federal gauge amplifier that originally used a 5.4 volt mercury battery. Those batteries are now unobtainium because mercury, so we're left to come up with a modern replacement. Now, I built a new battery pack using alkaline C cells, but this has a couple of disadvantages. One is that the voltage of the alkalines isn't as stable as the old mercury batteries, and the other is that people lose their freaking minds in the comments about alkaline batteries leaking and ruining my beautiful vintage gear. And they're right, so let's make something better. This is the gauge amplifier I showed in the previous video. Let's just disassemble it and take out the battery. Now, I was really proud of myself because I built the replacement battery pack into the original box that somebody had built an iCAD pack into that had come from the original mercury battery. And I thought that was really cool, but like I said, I got all kinds of feedback in the comments about these alkaline batteries leaking, and yeah, that really is a concern. So let's see if we can figure out something better than alkaline batteries. The other problem with the alkaline batteries besides leaking is the voltage curve. I've got the data sheet here for a similar battery, and you can see that as the battery's in service, the voltage drops. It starts out at about 1.5 volts per cell and goes down to under a volt per cell by the time it's fully discharged. The old mercury batteries didn't do this. They had a pretty flat curve. Now, the closest thing we have today is something like these lithium batteries. They have a 20-year shelf life, and on the back it says they are 100% leak-proof, and since it says it on the package, I'm sure it's true. If we look at the data sheet for these cells, you can see that the voltage discharge curve is actually much better. At 10 milliamps, which is about what we'll be using, you can see it's pretty flat, starting out, they say, around 1.5 volts and dropping to about 1.4 by the time we get out to 3,000 milliamp hours of capacity. But let's see what they're really outputting right from the box. Just put 4 in a pack and hook up to the voltmeter. And yeah, 7.25 volts is pretty high. I'm not really comfortable putting that into an instrument designed for 5.4 volts. So the obvious solution is a voltage regulator. Now, if you spend any time around electronics as a hobby, you'll know what this is. It takes voltage in on one pin, connects to ground or an adjustment resistor network, and outputs a lower voltage on the third pin. But as usual, there are always trade-offs. This is a typical hobbyist-friendly voltage regulator, the LM317. This is a 3-terminal adjustable regulator. So the voltage goes in on pin 1, pin 2 goes to a resistor network that adjusts the output voltage, and that adjusted output voltage comes out of pin number 3. Now, the main issue with this for this application is that it is always going to draw current from the batteries even when the device is turned off, unless we put in an additional switch, which I don't want to do. There will always be current flowing out of the adjustment pin and additional current flowing through the adjustment resistors. Well, how much? The adjustment pin could flow up to 100 microamps, and so you need the current in the adjustment resistors to be at least 10 times this so it doesn't affect it. So minimum, we're going to have at least 1 milliamp flowing continuously, and that's going to drain those batteries in less than a year, even if that's all it was, and typically it's going to actually be more than that. Now, I could add an additional switch that you have to turn on to switch on the battery to the regulator, or I could rewire the device so that the switch is between the battery and the new regulator, but I really don't want to mess with it. The other big issue with this is the dropout voltage, and that is the difference between the input and the output. So at typical kind of room temperature at low currents, there's going to be more than 1.5 volts of drop, meaning that for a 5.4 volt output, we've got to have at least 6.9 volts input, and we don't have that from the 4 AA's. However, I got a tip in the comments of the last video about a very specific TI regulator that looks like a much better fit for this application. The TPS-7A25 is a family of ultra-low quiescent current, low dropout linear voltage regulators. So it should not draw a lot of current when the load is off, and it should have a very low dropout voltage. You can see it has a few more pins and the circuit is a little bit more complex, but the concept is the same. Let's take a look at the specs and see how this works. The feedback pin current here is 10 nanoamps. That is so much better. That means we should be able to get the resistor network down in the 100 nanoamp or at most 1 microamp range. And the dropout voltage at low currents is less than 100 millivolts, like maybe 50 or 60 millivolts. That also sounds fantastic. So what's the catch? Well, the catch is it's a very small package with 7 pins on the bottom. This package is 2 millimeters on a side square, which means we're not going to be soldering this by hand. We're going to have to make a circuit board for it. But don't worry, I got you. All we have to do is replicate this circuit from the datasheet. Now I have switched over and I'm doing all new circuit board designs in KiCad. I do like it a lot better than Circuit Maker. I've just transcribed the schematic into here. The one change I've made is I've split the upper resistor in the divider into 2 separate resistors in series. This allows me to get to the resistance values I need for 5.4 volts without having to go to more expensive exotic components. I can just use off-the-shelf 1% parts. Now I transferred this over and laid it out on a small PC board. This ended up being pretty simple. It's 13.5 by 22 millimeters square. And if I pop up a 3D view here, you can see a little bit better what's going on. The regulator here is the star of the show, and this has got 7 pins on it, 6 on the sides and a pad in the center underneath. And then I've got 4 I/O pins. The top 2 are for the battery voltage in and ground, and the bottom 2 are for the output voltage, 5.4 volts, and ground. There's nothing on the back because it's a very simple circuit. No V is required. It's a pretty simple layout. Now, if I hide the regulator, you can see that in addition to the 6 pins around the periphery, there's a pad in the center, and that is for heat sink. And you can see it's connected to copper pores on the board, and that's how this chip rejects heat, is by using the copper on the board. This should be plenty for the kinds of currents that we're going to run, but in fact, it's probably overkill, and I did that so that this would be usable in other devices and not just the one that I'm retrofitting. I'll send this design off to the fab, but I'd like to keep working on the project, so I will output a step file, which is a 3D model, and that'll allow me to work with the board and even 3D print a sample of the board that I can use for test fitting while I wait for the real circuit boards to come back from the fab. Now, I'd like to fit everything neatly into the space that was originally occupied by the Mercury battery. So I've got my battery holder, I've got my circuit board. This is the 3D print that I made from the step file. As you can see, those components are pretty small. 2 by 2 millimeters is not a lot of space to solder 7 connections. And then I've got the cable that comes out from the original battery going to the unit that I would like to reuse. So I've got to make something that'll fit everything in here. I will just measure this compartment and we'll go design something on the computer and 3D print it to hold everything, including this connector plate that should fit up with the battery terminal that's already on the device. I spent some quality time in Fusion 360 and this is what I came up with. This is a printed plastic box. You can see some spring tabs up there at the top to keep it from rattling around. And then it's got space in it to hold the battery holder and the circuit board. And then there's a slot up here in the front to hold the battery connector plate. Let me turn a few of these things off and you can see there are little platforms for the circuit board and the battery holder with threaded inserts so they can be screwed down. Those are for M3 screws. Now I'm not going to go through the entire process of modeling this, but I will show you some of the highlights to get you started if you want to do a project like this. So to make the box, I'm just going to start by sketching a rectangle, setting the dimensions. I'll hit D for dimension and add the correct dimensions to the sketch. Then I'll just finish the sketch, select it, hit E to extrude, and pull this up into a 3-dimensional box. Now, before I go any further, I'll hit F for fillet and round some of these corners. I'm doing that before I hollow it out so that I can get a consistent wall thickness all the way around. Now, to hollow this out, I will use the shell command, select the top of the box, enter the wall thickness, and presto, we have a hollow box. So now I'm going to drag in 3D models for the battery holder and the circuit board. The battery holder, I got to save this before I can pull in another model. The battery holder I found on GrabCAD and made some minor adjustments to get the size correct. And then of course the regulator PC board is just from that step file that I exported. I'll just drag those in and I'll just let them land wherever they land. Now I'm going to hit J for joint, click the center of the bottom of the holder, click the center of the bottom of the box, and it will position them together. And then I can use the offset arrows here to move it around to where I want it. Now I don't want it on the bottom of the box. I'll pull it up. I'll type in a value of 8 millimeters. I think that's about right. That's where I'm going to want that battery holder. Now I'll do the same thing for the circuit board. Hit J, select the center of the bottom of that, select the center of the bottom of the box, and then move this around to about where I want it as well. And we'll pull it up 8 millimeters off the bottom. Now those wires are going to interfere. I'd like to pull that down. I'll just double click and adjust that joint. And that looks about right. That's where I want it. Now to support these parts in space, I'll construct an offset plane, click the bottom of the box, pull that up 8 millimeters, then right click on it and say create sketch. And this will give me a place to sketch geometry to support that. Turn the actual box off, hit P for project, select the bottom of these components. And now if I turn them off, you can see that I now have a sketch floating 8 millimeters off the bottom of the box with reference geometry I can use. So then it's just a matter of using the offset tool, like hit O here and pull it out from the sides of the battery holder, select the perimeter of the PC board, pull that out, and I can construct all the geometry I need here. Then I can do things like select these regions, hit E for extrude, say to object, click the bottom of the box, and presto, I've just made a platform to put the battery holder on. I can do the same thing for the circuit board. I can put ridges around the edges. I can dig out a trench for the battery wires. It's just a matter of sketching and extruding down to the bottom of the box. Now for these spring tabs, I just sketched on the side where I wanted those, hit E for extrude, and cut those through the side of the box. Then to put the spring tabs back in there, I created a new midplane, just selecting the ends of the box and creating that in the center. Right-clicked on it, created a sketch, and sketched in the geometry of that spring tab. Then I can select that region and I can extrude it, starting with the start at object, and then I can select the edge of the hole, offset that 1 millimeter as my start point, and then distance of 13 millimeters, and I get that spring tab. Put some fillets on it, and then use the mirror feature command to mirror that tab I just created over into the other hole as well, and now I've got 2 spring tabs to keep this box from rattling around in the hole. So there are a few little tips. I'm not going to model the whole thing. Those videos tend to get pretty long and not a lot of people watch them. If you're interested in that, let me know in the comments and I would consider it. But for now, I'm going to 3D print this and we can go see how everything fits. I'm printing this in ABS on the Bamboo Lab X1 Carbon. ABS should be plenty for this. It'll be flexible. It shouldn't fracture. If I need the strength later, I can reprint it in nylon, but ABS is cheap and it should be fine for this application. I chose the hole size in the part here to accept these M3 threaded heat set brass inserts. So I'll just press those into the hole and then we'll melt them into the plastic with a press. Now this particular heat set insert press is the one that Naomi Wu sells in her online shop. It is totally not necessary to use something like this. You can do this easily with a soldering iron. But if you have a lot of these to do, a press like this is pretty nice. It is spring-loaded, or rather rubber band loaded, and you set the depth so it presses it to a predetermined depth and stops, and it always makes sure that they go in nice and square. And that's that. Now we've got some nice solid brass threads in here. We can put the screws in and out as often as we want without worrying about tearing up the plastic. Think everything will fit? I think everything will fit. So you can see I put a little groove in the back here for the battery wires because they don't come out in a convenient location. The battery holder fits in there. I've got a little ridge around the side to locate it, and we'll put this in with 2 flathead M3 screws. Now I found with these particular inserts I have that I have to turn the screw backwards until it clicks over one thread to get it aligned, or sometimes they cross thread. Those go in nice and neat, and then we'll put the dummy circuit board in here with some M3 button head screws. Looks like I got that wire terminated at about the right length. I mean, we'll see when we get the real pins. Then I've got the battery connector with some wires on it and a similar little header connector. Now it looks like I guessed about right on those wires. Okay, so far so good. Let's see if this fits in the instrument. Now I will admit I didn't like the fit the first time around, so I made a minor adjustment and reprinted this. Just checking to make sure the battery terminals really are the correct direction. I don't want to reverse the polarity. And that fit is nice, and those little spring tabs are keeping it from rolling around in there. Now, the first fit was okay, but it didn't have enough pressure on the spring tabs, so what I changed is I gave them another millimeter of extension just so that the spring would be a little bit tighter. That looks good. Now we just have to wait for the circuit boards. Hey, the boards are back from the fab. Let's see what we've got. Now, I didn't order just one, I ordered several because I know several of you are going to pop in the comments and ask me if you can get one, and the answer is yes, you'll be able to get one. So they've got them all stuck together here with a piece of Kapton tape, and the first thing that I notice is that one of them is backwards on the tape. Seems like a very chaotic neutral thing to do, but it doesn't matter. Let's get one hooked up and see if it works. See if I screwed up the circuit board and if I did my math right on the resistors. I'm going to hook up my bench power supply here to provide the input voltage to simulate the batteries, and I'm going to measure the output voltage using a 6.5 digit voltmeter. Voltmeter? That's not a word. Okay, 7.5 volts in. It looks like we're getting just over 5.4 volts out, which is exactly what we want. So I did do the math right on the resistors. Now the interesting question is, what does this do under a load? So I've got a digital electronic load over here, and we'll hook that up to the output and simulate the instrument and see what this thing does when we start drawing current through it. Now, I really don't like the terminals on these things. I know why they're this way, but I can't just put banana clips in them. So I'm just going to yank the nuts off and just use alligator clips. And then I'll hook this up in parallel to the voltmeter. We'll switch it on. Still got our 5.4 volts of output, and we'll program the load to pull the 10 milliamps that will be required for the gauge amplifiers, 0.01 amps, and we'll switch it on. Okay, we're drawing 10 milliamps. The instrumentation on the power supply is a little bit off, but we're still holding about 5.4 volts. There's a tiny bit of voltage drop there, and I think that's just because of how I have it wired. Let's go ahead and see what this does under a higher load. Let's try 50 milliamps. And yeah, the measured voltage is dropping a little bit further. I think it's because of the wires, because I'm measuring at the end of the wires after they've carried the load. So we're seeing that voltage drop. Try 100 milliamps, and yeah, we're getting even more voltage drop. Let me rewire this so that I'm measuring at the output of the regulator and not after the wires that are carrying the current to the load. Switch this back on, and there we are, 100 milliamps, and we're still holding strong at 5.4 volts. And we're seeing the lower voltage at the load, but measuring at the board, we're still seeing 5.4. Let's go ahead and bump this up to 200 milliamps. That's still great. We've dropped 2 millivolts. That's just fine. And let's try 300 milliamps, which is the limit for this regulator. Now, I'm not sure I have the thermal capacity to really do this, but it's certainly doing it, at least in the short term. Let me feel this and see if it's getting hot. Yeah, there's a little heat. I would need to do some long-term testing to see if I would rate it for that. The reason the voltage dropped when I touched it is because the resistance on the voltage divider is so high that my skin contact was affecting the feedback voltage. Let's try measuring the dropout voltage and just see how low we can go. I've got this set up with 7.5 volts of input, of course 5.4 volts output. That's about 2.1 volts of drop across the regulator. And let's just dial the input voltage down and see how low we can go. Let's get this all the way down to a dropout of 66 millivolts. We're still holding strong. We'll dial this down a little bit further. We're down to 5.5 volts of input, and we're still holding strong. Go down, so we've got a dropout here now of 46 millivolts, and we're just starting to see the output affected. That's actually quite good. Let's see how much further we can go. There's 36 millivolts of dropout, and we're still holding pretty close. This would totally work, though it's getting sillier by the moment. 26 millivolts of dropout, and yeah, we're down, what, about 10 millivolts on the output. This is really the limit, but that is fantastic performance for this little regulator. Let's do one more thing, and that is to measure the quiescent current. So this is the current that the regulator will draw if we just leave it hooked up to the battery with the instrument turned off. Go ahead and switch this on and see how much it draws, and I see nothing. Why is that? Oh, it's because I forgot to switch over to the current terminal. Let's try that again. 7.5 volts in, and it is drawing 3.3 microamps DC. This is fantastic. We could leave this connected to these batteries basically forever, and it'll have no real appreciable effect on them. These batteries have a marked 20-year shelf life, and over 20 years, this level of current draw will draw about 20% of the battery capacity, leaving about 270 operating hours out of the 300 that they would support while new. And that is fantastic for this application. We can just leave this thing plugged in virtually forever. Let's swap in the real board for this 3D printed prototype, and let's test this thing. Just pull the 2 screws, pull out the plastic board. I'll go ahead and connect these wires before I put it in, just so that I can look carefully at what I'm doing. Snap that down to place, put the screws back, and we should be ready to go. I'm looking at this very carefully to try to make sure that I have the positive to the positive. I really do not want to fry anything in the real instrument. I can't really get another one of those. They don't make them anymore. Well, they do. They don't make the vintage ones anymore. Let's try checking the output voltage here. There we are, 5.4 volts. Looks like the polarity is correct. Let me check my input terminals. Yeah, those look to be correct. And it looks like we've got 5.4 volts. So this is a simulation of the original Mercury battery. I don't think there's anything else I can check. I think it's time to just put this in the instrument and try it. We already know this is going to fit here in the instrument. I'm going to check one more time and make sure the positive is lined up with the positive. I'm just deathly afraid of doing something dumb here and frying this. That fits as expected. Make sure the wires are tucked out of the way. Don't want to pinch anything. And let's just put the back on. There's no reason to expect anything to be wrong with this. So we'll just go ahead and put it together, seal it up, and reconnect the gauge head. I'm nervous, but I don't think there's anything else I can check. Let's just power this thing on and see what happens. And that looks promising. Gain's a little bit high because I adjusted it for the cartridge gauge head last time I used it, and also I had the alkaline batteries in at a different voltage. So I'll just adjust this and try to get this right in the middle of the gain range. And it's worth setting this carefully because it's a regulated voltage. It should stay indefinitely. That looks pretty good. Let me grab the gauge head off the back and let's see if it actually works. Of course, the clip is outsmarting me, so I've got to get past that hurdle. Then just turn it on. Yep, gain's still in the right place, and it works. There's really no reason to test this anymore at this point. I can see that it is operating correctly, but I'll go ahead and run it through the ranges, mostly just because it's so much fun to play with. I don't know what it is about this vintage gear, but I could just sit here and play with this for hours. I'll go ahead and do that, but I won't make you watch it. I'll go ahead and send you on to the end of the video. I know this is a common problem that many people face, so I ordered 30 of the boards, and I will make the extras available for sale. There will be a link down in the video description. I have no idea how much interest there will be, but if this is something that people want and they sell out quickly, I'll make more. If you enjoyed this video or found it useful, give it a like, subscribe, and maybe think about supporting the channel over on Patreon. Patrons can download files for all of my projects, including this one, and get a little peek behind the scenes. Thank you for watching.